Okay, if you're like me, you don't own a bowling ball, you don't own bowling shoes, but you don't mind going once, maybe a year with your friends. Right, so the question is, say I'm bowling with my friends, I pick out that nice heavy bowling ball, because that's the manly thing to do. I bowl the first game, I'm doing great. By the second game, the third game, right, I start having like the lightest ball possible because my arm's getting tired, I'm not able to send the ball as fast. What is happening? What's the physics behind that? It has everything to do with Newton's second law of motion. So what is Newton's second law of motion? It's also known as the law of acceleration. Let's take a look at it. So basically it states the acceleration of an object depends on the mass of the object and the amount of force applied. Okay, let's break that down. So when I'm moving that bowling ball down the alley, that speed that it's building, that acceleration that it has going down the alley, has everything to do with how much that ball weighs and the force that's being applied. So as the night goes on, as I start bowling, the force goes down, right? My muscles are getting tired. What doesn't change is the weight of that bowling ball. So think about it. As I bowl and I bowl, as the force gets less, the acceleration gets less. So by the end of the night, if I want that ball to go the same speed, I'm gonna have to, since I'm decreasing my force, I need to decrease the amount of mass of the bowling ball, right? So that's why by the end of the night, I'm bowling probably with the lightest ball out there in order to kind of keep that same speed, right? Which has its later impacts, right? Think about it, a heavy bowling ball is probably gonna be able to knock the pins over a lot easier than a lighter bowling ball, right? Think about it, regardless of how fast it's going, right? A heavier one, if it's going the same speed, right, it's gonna be able to knock those things down a lot easier. Much like a bus is gonna be able to knock down a lot more things than a fly going the same speed. All right, so let's look at the nitty-gritty behind this. There is an equation for this Newton's law, right? It is force equals mass times acceleration. Again, so force equals mass times acceleration. So let's take a look at a couple examples here. Let's talk this through, much like we did with the bowling. So suppose this year, right, maybe you're still in school and you do the good old mile run, right? One of my favorites, 4 laps around the track, or maybe you have a mean gym teacher that makes you run like 30, 40 laps around a smaller area, which is just brutal, especially if you can't count that high when running. However, imagine you're doing the mile run, except this year they're like, hey, let's add on a nice little backpack that weighs like 40 pounds. Welcome to boot camp, all right? So why is it harder? Again, if we look at that equation, right, force, we're kind of giving it our all. So that's something that doesn't change. What does change is, if you look at that equation, force equals mass times acceleration, right, that mass changes. Right, so if what our end result is going to be the same, us exerting so much force, if the mass changes, the acceleration changes. So as the mass goes up, right, our acceleration, how fast we're taking off, is actually going down. Right, so that makes sense, right? We'd have to actually use a lot more force to start moving around the track, right, or to complete that mile. So those of you guys interested in boot camp, make sure you're training with a lot more weight. A good example of this also, we could look at just this picture of a train, all right? So the first picture of the train, right, we have one engine in the front and we have one cart behind it, okay? Now, if you look at our vector, which shows us our magnitude direction, it's pretty big, right? Our train's able to move pretty quickly. What happens though is when we add another cart behind it. So now we have an engine with 2 carts. Say we double the mass. What's gonna happen is, right, our train is not able to move as quickly, as easily, right? We're gonna have to use a lot more force if we want to go the same speed. So that's what we did in that third picture. We added another engine, and what does that do? Now we can kind of get back to that same speed, the same acceleration down the track, because we doubled the force when we doubled the mass. Okay, hopefully you kind of see how this equation's working out. And we can see this example in a lot of different ways. Take, for example, weightlifting, right? If I'm just using a barbell and I'm doing bench press, all right, I'm pressing it out, right? Pretty easy, right? I can do it pretty quickly. Now, if I add weight, what happens, right? It becomes more of a struggle, right? As the mass increases, right, the acceleration is going to go down with the same amount of force. If I want to go the same speed, I'm going to have to apply a lot more force. And quite frankly, I probably don't have that. So that's going to become a problem, or I'm going to have somebody else help me, and now there's two people squatting the same barbell, which would be weird. The same thing can be said about, say, a empty grocery cart, right? So maybe you dabble in some grocery cart racing outside of Walmart's parking lots, right? You jump in the cart, you're moving, you're using a nice little broom to push yourself down. If you weigh more, or the cart weighs more, you're going to do a lot more force, a lot more pushing to get that cart moving, right? Or maybe you're just an inside Walmart grocery cart racer, right? You're pushing an empty grocery cart. It's so easy to kind of start flying down and running behind it, whereas you got to put a lot more grunt work into pushing a full grocery cart. But here's what happens. As much as you need more force to get that full grocery cart moving, now think about stopping that grocery cart, right? To stop an empty grocery cart, right, I could probably use one hand. To stop a full loaded grocery cart, it's going to take a lot more force. The same thing happens. Despite taking more force to get it moving, once they're moving, it takes more force to stop it as well. It almost has more momentum, right? More building up to it, right? I could stop a mosquito going 5 miles per hour pretty easy with a hand, right? Just swat it down. Stopping a bus going 5 miles per hour, right? It has a whole lot more mass, right? It's moving the same speed. It's going to take a lot more force to stop it and to restart it, to get it moving, okay? So hopefully this is starting to kind of make sense. We could look at that equation over and over to kind of get a better idea. So if I want to break this down into an example of, say, a word problem. All right, take this. So if you are used to going to the circus, which has really kind of died down. I guess we got Circus Soleil, but one of the favorite things of Barnum and Bailey was this idea of a human cannonball. So basically a guy wedged himself into a cannon, right? They loaded it and whoosh, they launched it off, and there goes a guy right across the entire gymnasium arena. So here we go, here's the problem. So how much force is needed to project a 35 kilogram man out of a human cannon at a rate of 5 meters per second squared? So let's look at our equation. So we want force, so that's F equals, and we have mass times acceleration. We have a mass here, so 35 kilograms, right? And we're looking at shooting him out at a rate of 5 meters per second squared. So all we need to do is multiply. So 35 times 5, and we get an answer of 175 newtons. Don't forget, forces measured in newtons. All right, let's take a look at another problem. So here we have a speeding train. It says how much force is needed to slow. So this time, instead of pushing, right, maybe we're pushing to slow or pulling back a train. So how much force is needed to slow a 500 kilogram train by a rate of 4 meters per second squared? So we're trying to slow it down, right? Same thing. So force equals mass times acceleration. We have a mass of 500 kilograms times 4 meters per second squared. And what do we get as our end result? We end up getting 2,000 newtons, right? That's what's going to be needed to slow down that train. Okay, we'd have to constantly apply that. Okay, a soccer ball, much lighter. Okay, thankfully, much lighter than a train, right? A soccer ball has a mass of 0.5 kilograms. Okay, so we have that mass. How much force is needed to accelerate the ball at 4 meters per second squared? Right, so same thing. Hopefully you're catching the trend. Right, to find the amount of force, we're looking at mass times the acceleration, so 0.5 times 4, and we end up with 2 newtons. Okay, our last problem here has to do with volleyball, right? So if volleyball has a mass of 0.25 kilograms, so that ball is actually about half the weight of an actual soccer ball, and a player generates 30 newtons of force. Okay, so now we have the force, we have the mass. What we're missing is the acceleration. It says, what is the acceleration of the volleyball? How fast is it speeding up? All right, so let's take a look. So we have, in our equation, we have 30 newtons equals 0.25 times the acceleration. So that's the variable. So in this case, we're going to have to take the 30 newtons divided by 0.25 to get our acceleration alone. And that should equal 30 divided by 0.25, 120 meters per second squared. Right, so you see how we can kind of go back and forth with this equation. At the end of the day, again, let's keep in mind what we're talking about. Right? For example, if I'm doing shot put, right, that nice heavy ball, if I'm exerting all the force I can, if it's lighter, I'm going to be able to make that speed up. If I'm trying to get a heavier ball to move the same speed, or the same acceleration, I'm going to have to apply a lot more force. And that goes with everything. As we talk about Newton's laws, right, these are basically natural laws that they make sense, but now we're finally putting it into words to understand what is the physics behind it. So next time you pick up a bowling ball, hopefully you remember that, yeah, by the end of the night you might start with a heavy one, but by the end of the night you're going to be with the lighter one. Or maybe you're going to take that approach, kind of like the tortoise and the hare. You're going to start with a medium-sized ball, and hopefully you'll be able to make it a few games going the same speed and not wear yourself out as much as I do. So thanks for watching. Hopefully you guys subscribe, and we'll see you next time for Newton's third law.